this section we are going to look at mechanical translational system, and we need to find the state space equivalent of the system. And the way we are going to do it, just like in the previous sections, we are going to look at energy storage, and energy storage will be in the springs and in the mass as well, meaning that we can select. Let's write down the equation of motion first. We have mx double dot plus bx dot plus kx is equal to our applied force. This can also be written as, because we know x double dot is v dot, so mv dot, this is in terms of velocity, plus bv plus kx is equal to applied force. We can select the state to be the velocity and the displacement. So we'll choose the displacement to be a state and v to be our another state. And we say that we need to find the derivative of our state. So we need to find the derivative of that, and we need to find the derivative of that. So we know from Newton's law, x dot is equal to v, and v dot, from here we are just going to take this equation and take it on this side. So we can write that as v dot is applied force minus bv minus kx times 1 over m, because I took the m outside on the other side. Okay, from there we can just write the state variables by stacking this together. So I have x dot, we have v dot is equal to, we said our state variables were x and v, and we say that x dot is equal to v, so we have 0 here and 1 there, and v dot was on x we have minus k over m, and at v we have minus b over m. I'm writing this information, okay? And our input is our force, and this force was you have a 0 here and 1 over m. So as we can see, it's very, very straightforward to write a state equation of a mass spring damper, because you just choose your state variable to be v, which is your velocity, and x, which is your displacement, and you find the derivative of this state variable and you solve the equation. Let me look at another example. Here's another example whereby we have the system with two masses, and we want to derive the state space model for the system. And what we can do is we can select our state variable to be x1, v1, x2, and v2. So before I do that, before I go further, let me write the modeling equation, the system's equation. Let's say we have m1 x1 double dot plus bx1 dot plus kx1 minus kx2 is equal to 0, and the second one we have m2 x2 double dot plus kx2 minus kx1 is equal to our applied force. And remember, I've chosen the state variable to be x1, v1, x2, and v2. Now, we need to find the derivative of those. Let me just write them down properly. So, we have x1, we have v1, we have x2, we have v2. And we said we need to find the derivative of that, of that, of that, of that. We know x1 dot is equal to v1, and v1 dot, we are going to solve this equation. Let me rewrite it. So this is going to be m1 v1 dot plus b v1 plus kx1 minus kx2 is equal to 0, whereby v1 dot is equal to, I'm going to put everything on the other side now. Okay, so we are going to have 1. So we take the b on the other side minus b v1 minus kx1 plus kx2. Okay, so we have v1, so I'm going to write this v1 here. So we say v1 is 1 over m1 times b v1 minus kx1 plus kx2. Okay, next we need to find our x2 dot. It's easy to say x2 dot is equal to v2, so we can just say x2 dot is equal to v2, and this is true. And our v2 dot, we need to solve this equation. Let me use a different color. Let me use the green. I'm going to rewrite this one here. So we have m2 v2 dot plus kx2 minus kx1 is equal to our applied force. Hence, we can say that v2 dot is equal to 1 over m2 applied force minus kx2 plus kx1. Okay, so I'm going to bring this here to rewrite it here. So we have 1 over m2 times our applied force minus kx2 plus kx1. Okay, now we are ready to write our state equation down in matrix form. All right, so let me just make some room. So I can write my big matrix here. We are going to have x1 dot, v1 dot, x2 dot, v2 dot. This is equal to, let me just make enough room, x1, x2, x3, and x4 are my state variable, plus some input times our applied force. For x1 dot, we say x1 dot was, oh, I made a mistake here. I need to write, we have x1 and v1, not x2. So this is v1 and the other one is v2. X1, v1, x2, v2. Okay. For x1, we know that x1 dot is equal to v1, meaning that you are going to have 0, 1, 0, 0. v1 dot, we are going to have minus k over m1 minus b over m1. Then we have k over m. Then we have 0. Okay, for x1 we have minus k over m1. v1 we have minus b m1. x2 we have k over m. v2 we don't have anything, hence is 0. Okay, the next one for x2 is equal to v2, and v2 is somewhere at the last, so we are going to have 0, 0, 0, 1. So we just distribute the zeros across. Then we write for v2, which is this equation here. v2 at x1 we have k over m2, k over m2. Then for v1 there is nothing. For x2 we have minus k and m2, minus k over m2. And the next one is v2. there is no v2, and this is 0. And our output equation, our input is the applied force, which is at v2, which is the last column. So we are just going to write 0, 0, 0, and 1 over m2. And what was our output? We were not asked about the output, but let's say, for example, we should always have an output. What do you want to be our output? Let the output, I think in the book the output was v2. So let's assume that the output is v2. So we want v2 to be our output. So again, we are going to write our matrix output form. So we have x1 v1, x2 v2. And we are just going to distribute a 0 at x1, 0 at v1, 0 at v2, and 1 at v2. So this is our final result.